All right, well, welcome back. Now we're going to finish up chapter 3 material. We've found the density of states function. We're actually going to put off the combination of these things till next chapter, but we've looked at the density of states. We saw that G of E goes as the square root of energy. That's the number of states per unit volume per unit energy. Well, and I mentioned before that we're going to look at the probability that a state is occupied. All right, so that's where we are today. Statistical mechanics. There are, well, statistical mechanics is involved when we're interested not in an individual particle, but we have lots of particles and we want to know their kind of overall behavior in a statistical, aggregate, kind of average sense, you might say. So, in statistical mechanics, just for reference, there are three distribution laws. And I'll name them, talk briefly about them, but we're going to focus on one and then two because two of them are related for what we need. The first one is one that we will end up using, but we have to justify its use based. Well, let's see how that works. Maxwell-Boltzmann. These are names that we are familiar with. The Maxwell-Boltzmann distribution, it's really a classical, it's applied in classical physics. Particles are considered distinguishable in the sense that you could say this electron is different from that electron, and you could identify them, count them, and see how they all work in an average sense. There is, in the Maxwell-Boltzmann, no limit to the number of particles in each energy state, so that would not be consistent with the Pauli exclusion principle. Gas molecules at low pressure follow this law. And again, this is prominent in classical physics. You know, these guys were classical physicists. Boltzmann getting into quantum mechanics at the early stages. So Maxwell-Boltzmann, we'll actually end up using this, but we'll have to justify it as an approximation for our purposes. The next one, so again, Maxwell-Boltzmann works for gas molecules at low pressure. The next one, Bose-Einstein, named for two physicists, Bose and famous Einstein. Here, particles are indistinguishable, which this is going to be really counterintuitive for us. Here, it makes sense that you could be able to distinguish between different particles, different atoms, molecules, electrons. Here, you cannot. One looks just like another. And there is no limit to the number that can occupy a state. So this is not like an electron, as we've said with the Pauli exclusion principle already. But photons are like this. In fact, photons do follow Bose-Einstein statistics. They are indistinguishable, and there's no limit to the number of bosons that can occupy a state. Again, photons and black body radiation follow Bose-Einstein statistics. And the third one, which is, of course, the one that we're going to have to deal with, we'll end up getting back to Maxwell-Boltzmann, but it officially, formally, Fermi-Dirac, or Fermi-Dirac. Fermi-Dirac statistics are for particles that are indistinguishable. How about that? Electrons and holes are going to be indistinguishable. So it's like Bose-Einstein in the sense that particles on the subatomic level, quantum mechanical effects and all this, the particles are indistinguishable. However, you can only have one particle per quantum state. As we said, they are fermions. And again, the Pauli exclusion principle is built in right there. Now, our author, Niemann, actually does outline the development of this, but we're just going to take this as a postulate, as a given. It comes from some kind of deep thermodynamic considerations, but what we have is the Fermi-Dirac distribution. F for, I don't know, we just use F for a distribution function here, or energy function. And then sub F for Fermi. Sometimes I've seen this F sub D for Dirac, but either one works. It is a function of energy, and here it is. 1 over 1 plus the exponential function e minus e sub f over k, let's say k sub b t. All right, what are these terms? What are these terms? Well, we know what the exponential function is. E is energy. K sub b, I've put a subscript b on there to indicate that is the Boltzmann constant, not our wave number k that we've been dealing with particles. But this is the Boltzmann constant. T is the absolute temperature, so kT, k sub bt. E sub f is something that is a new quantity. E sub f is something called the Fermi energy, or the Fermi level. Named after the physicist Fermi, Enrico Fermi, is an Italian. What this function is, it is dimensionless, and it is called the Fermi-Dirac distribution. However, or probability function, or the Fermi-Dirac probability function. The Fermi level is obviously an important parameter, which we'll talk more about. But at this point, we want to get a sense of what the shape of what this generally means, and the shape of it, how to understand what it's talking about. Okay, so it is dimensionless. It is also the second formula on our basic equations for semiconductor operations sheet. We have this, if you look at that on Moodle Rooms, we've got several equations or sets of equations up through Maxwell's equations. So this is our second one. The first one was the Schrödinger equation. That was our first basic equation for semiconductor device operation. And the second one is the Fermi-Dirac distribution, the Fermi-Dirac probability function. F sub f, a function of E, it's 1 over 1 plus e to the energy minus e sub f over kBt. Although on the sheet it's called k, but I'm indicating that is the Boltzmann constant, not wave number, Boltzmann constant. All right, so we get to our second key equation here. It is the ratio of the number of filled quantum states to the total number of quantum states at any given energy E. Now, if you have a whole lot, then that's going to be the same as the statistical probability that the state is occupied. What this is not, here's the thing what this is not. It is not a probability density where you integrate over all, in this case, energy, and it integrates to 1. That's not what this does. What it is if you want to know what is the probability that a state of energy E is occupied, you plug in that value of E, and it gives you a number. That's the probability that the state is occupied. Clearly, it's going to be related to the Fermi level. Is it above the Fermi level? Is it below the Fermi level? Is it equal to the Fermi level? It's going to be, so the Fermi level is going to be an important parameter. But given the Fermi level, this tells you the probability that a state with a certain energy is occupied. So probability that state is occupied. What does this thing look like? Just generally, what does this thing look like? I guess I can also point out, K sub B, just to be completely clear, once again, K sub B is our Boltzmann constant. It has the unit, the value 1.38 times 10 to the minus 23rd joules per Kelvin. And that's equal to 8.62 times 10 to the minus 5th electron volts per Kelvin. Again, that's our K here, is our Boltzmann constant. Now, this is obviously a function of temperature, and we can relate things to the Fermi level. So let's plot this kind of qualitatively versus energy at different temperatures. So here's our Fermi-Dirac distribution. We'll put right here our Fermi level, or Fermi energy. And go down here to 0. Now, at T equals absolute 0, if you look at our function, the Fermi-Dirac function, what you're going to see is that for energy less than the Fermi energy, it's exactly equal to 1. And then for energies above it, it's 0. Okay, so this means that the probability at absolute 0 of a state with energy less than the Fermi energy of being occupied, the probability is equal to 1. It will be occupied. But the probability of it being occupied for an energy greater than the Fermi energy at absolute 0 is 0. It's not going to be occupied. So very simple for absolute 0. And if you plug in the Fermi level, Fermi energy, you get 1/2. If the energy is equal to the Fermi energy, the probability of it being occupied is 1/2. Well, as the temperature goes up, and I hope you can see my colors. I'm going to try to use some different colors here. As the temperature increases from absolute 0, we get this nice step kind of function here for absolute 0. As the temperature goes up, it gets to be smoother. So this is T greater than absolute 0. And it kind of gets flattened out, smoother and more kind of flattened out. We still end up at 1 here at 0 energy, and we go to 0 as energy gets a lot bigger than the Fermi energy. But we always go through. So if this is T1, say this is T2 greater than T1, greater than absolute 0. And it gets kind of smoothed out. That's what happens with our Fermi-Dirac distribution. So the probability is going down here. So this means as the temperature goes up, you have more of a greater chance of energy of the state above Fermi level being occupied, and less of a chance of the energy state below the Fermi level being occupied. That kind of makes sense. That makes sense. As temperature goes up, the particles have more energy, and so the likelihood that the higher energy states are occupied goes up, and the likelihood that the states at lower energy are occupied goes down. That makes sense. That would be the case. Now, because this is a probability and not a probability density, again, probability density would be if we integrated overall energy we get 1. But this is not the case. This would be if we had a probability density. This is not what we have. We have a probability function. And it's just giving us numbers between 0 and 1. It's a different thing. All right, so not a probability density, but is a probability function. What is the probability of a state not being occupied, of a state being empty? Well, if the Fermi-Dirac function tells us the probability that it is occupied, then the probability of a state being empty is 1 minus that. And that's going to be important for us. The probability the probability of a state being empty or not occupied is equal to 1 minus the value of the Fermi function for that energy. So if we want a function to say to give us the probability that a state is empty, that it's not occupied, that's 1 minus the Fermi function. Looking ahead, we will use the Fermi function for electrons because we're interested in states in the conduction band being occupied. We want to find electrons in states in the conduction band. But for the valence band, for holes, that's actually the absence of electrons. So we're actually going to want the probability that a state is empty. That would be where we have a hole. So we'll use this for holes, and we'll use the Fermi function for electrons. And we'll put that together in the next chapter. So there's our Fermi-Dirac distribution, our Fermi probability function. And again, we'll have more to say about this Fermi level. Obviously, it's a parameter. It's going to be important for us. But if we can just kind of get a sense of how this function works relative to it, then that'll be good for us right now.